Hello everybody. In this video we will train a neural network to classify handwritten digits as number 1, 2, 3 and so on, 0, 1, 2, 3, 4 up to 9, right? So the data set that we will be using today is the MNIST data set. So that is basically a collection of bunch of handwritten digits, and our neural network will try to classify them as 1, 2, 3, 4 and so on. So this is basically a hello world version of your deep learning programming, right? So if you are new for machine learning or deep learning, this is the introductions. How would you train a model? So I will use a convolutional neural network for this purposes. So this tutorial will cover basically all the codings. In the future, I will go deep dive into how convolutional neural network work, but for now, let's stay tuned. So for this one, obviously we need a bunch of packages. Again, you can do this in your Google Colab or other notebooks that you have, but right now I'm using Jupyter Notebook. So let's start with it. So let's say import NumPy as numpy, and from TensorFlow import Keras. We will be using Keras for our training purposes, and from Keras the data set. So this comes with oh no, from Keras just datasets, import MNIST. So Keras comes with the MNIST data built into it, so you can train by yourself. I think these are everything that we need. Okay, so let's load our data. So we got X train, Y train, and then we have X test and Y test equals to MNIST dot load data. Okay, so what this will do is this load data functions in Keras. It's gonna split our data sets into training sets and testing sets. So I'll show you in a second what these set contains. So let's run this once. So let's look at the shape of each data sets. Print xtrain dot shape and ytrain dot shape. And let's look at the testing sample as well. Print x test dot shape and y test dot shape. Okay, so if you notice here, so we have 60,000 training data sets, and there is a corresponding variable. So 60,000 handwritten digits and 60,000 sample, whether they are 0 or 1 or 2 or so on. And we have about 10,000 data sets that's part of our testing samples. And what this 28 and 28 represents is each handwritten digits is a 28 by 28 pixel. So 28 data sets. So each pixel corresponds to 28 and 28. So the pixel value varies between 0 to 25. So what we have to do is we have to, let me show you what this means. So let's say, so we get a print xtrain, and I'm gonna show only the first one, and then I'm gonna do a conversions. Xtrain equals to xtrain divided by 255, and then I'm gonna reprint the same one to show you the difference. So xtrain divided by, so I'm gonna show the exact first row, and I'm gonna do the same conversion for our testing sample as well. And I'll explain in a second why we are doing this. 255. Okay, everything looks good. So let's run. Okay, so you look at here, we are putting the first row. So in this case, what you see here is the pixel. So the numbers, so each data point, the number varies between 0 to 255. So that's the pixel values. And what we did here after conversions, we normalized this. So we normalize. So if you divide by 255, then the number will become something between 0 and 1. It's never going to be above 1. So you can see all the numbers get converted into corresponding values. So maybe if we can have something here. So let's see. It looks a little bit different. So maybe the first digit we had was 3. So this one here, the first digit is 3. So this one is basically 3. It should be 3 divided by 255. So we did the same thing. So by doing normalizations, our model will become better. Okay, so let's remove that portions. So I just kept it hidden so that it's not gonna take a lot of space. Okay, so now we did normalize our data set for training and testing sets purposes. Okay, now we're gonna change, we're gonna convert our Y train. So I wanna show you before and after. So print Y train for, let's say, the first 5. And then what we are doing here is we are gonna convert the Y train data sets into a binary matrix that's gonna be helpful to train our model. So Y train equals to Keras dot utils dot to categorical. So this needs 2 things. One is your data sets that you would try to convert, so which is Y train, the one that we had before right here. And then num classes, number of classes. So I put number of classes 10 because I know that all the handwritten digits could be one of the 10, right? So it could be 0, it could be 1, it could be 2, it could be 3, and it could be 9. So it could be one of those. So we have in total 10 different classes. And then I can show you how does the data looks before and after Y train. Let's say 5. So we want to see the same 5 numbers. So let's look at here. So the first number from our training data set was 5. So what we did here was we take 5 and convert it into matrix. So now we got the first column here stands for 0. Next one, 1, 2, 3, 4, 5th. So our 1, 2, 3, 4, 5th, 6th. So our 6th index here stands for 5. So this 5 means everything else is 0 and our 6th index is 1. So we converted 5 into a binary matrix. So this is our called one-hot encoding. And this one here, next one, let's look at 0. So 0 is our first index. So if you are new to the programming, we know the way we index in programming is the first one is always 0, 1, 2, 3, 4, and so on. So the first index is always 0. So this 0 means our first index is 1 and everything else is 0. And let's look at the 4. So 4 means our 5th index should be 1 and everything else should be 0. So you notice here this is 0, 1, 2, 3, and 4. So the 4th, which means the 5th index. This is the first index, second index, third index, 4th index, and the 5th index. So the 5th index is 1. And what's 5th index is? 5th index is number 4. You can do the same thing here, 1. So the 1 must be our second index. So this is our first index. This is our second index. So you see our second index is 1 and everything else is 0. So what we did here was we took our training data sets and converted into a matrix form with binary matrix. So I didn't do testing purposes because we're going to be using this to compare between either one of them. So I kept the testing as it is, so that will save one step of programming. Okay, so now let's build a model. So to build a model, we will be using Keras. So we need few things. So from Keras dot model import model, and then from Keras dot layers we're gonna import few things here. We're gonna be using conv1d, and then we're gonna be using batch normalizations. We're gonna be using dense, We're gonna be using flatten. We're gonna be using dropout. I think that's pretty much all we need. If we need anything later, I will import them. So from Keras dot engine dot input layer import input. Okay, so this time we are not using a sequential model. We are stacking model one after another. So so we have everything. Okay, so let's start here. So we're gonna start. So let's call this the first layer as our input layer. So for input layer, we're gonna input. So we're gonna be using the function that we just imported. It needs few things. Input layer equals to input shape. Dang it. So it needs few things. Shape. So what is the shape of our matrix? So if you go back, the shape of our matrix is 28 by 28. That's the size of the image. So it's 28 by 28. So we're gonna put that in there. So the shape is 28 by 28. All right, so we got our input layer. Okay, now we're gonna stack a bunch of convolutional networks. So I'm gonna calling this X. So that's gonna be our convolutional neural network. Okay, so here you can put shift and tab, then it'll show you all the variables that you need. I'm not gonna go too much into details today because each one of this variable it's gonna be one tutorial on its own. So in the future video, I will explain what kernel size, strides, and padding means. So I will so that I'll do definitely in the future videos when we talk about convolutional neural networks. So stay tuned. Okay, so let's start with filters. Again, this is something you can play around with it. Number that you would like. I know it works well around 32. You can do 64. I think 16 is okay too. I have seen. And then kernel size. So the way one way I would explain what is kernel size means, like they say, how would you eat an elephant? It's 1 byte at a time. So if you're doing image analysis, you're not gonna read the whole image. The computer not gonna read the whole thing. It's gonna read 1 byte at a time. So that small, like one portion of the image, it will analyze, then move to the next portion. So that's called kernel size. How many pixels or what are the sizes you are reading? Okay, so since this is we are doing 1D, we have a 1D numbers here. All right, so let's move on to the next one is strides. Strides, that's basically like once you eaten that 1 byte, like how would you eat an elephant? 1 byte at a time. So once you eaten that 1 byte, then you move to the next byte, right? So when you move, how many pixels you're gonna move by? So in this case, we are moving by 1. If you move 2 pixels, then your model will be a little bit bad, but it'll gonna be faster too. So let's do 1, and then padding equals to same. Again, this is gonna be a topic on its own, so I will explain that later. Filters, padding. Let's put the activation functions. I'll be doing a tutorial on all the different type of activations functions that we can use and what other activation functions are. So please stay tuned. So we will be using ReLU as activation. Now this convolutional layer is gonna work on the input layer. So it's gonna be working on the input layer. So that's why the last one is, it is working on who. So it's working on the input layer that we just entered. Okay, so I'm gonna add a few more layers. These are optional if you want. One is called batch normalizations with momentum. So batch normalization is kind of handy. Again, it's not necessary, but I have seen it improved by a percentage or 0.5 percentage point our accuracy score. But it's, so what it does is it's like, how would I explain this one? So what it does is it's called, when you train a neural network, some of the variables. It's the, dang it, this is trickier to explain. So it controls, so for example, let's say like you are trying to play a balance act, right? So you are trying to balance a long stick on your hand. And then what happened? So you are slowly moving your hand left to right so that the hand on the stick, the long stick, is staying balanced. But if you move too much, then it's fall off. But if you move just enough, then it'll stay balanced. So that's the purpose of batch normalization. It'll control the momentum of those variations so that the model will stay true. It'll stay as close as possible. But if you move too much, if the momentum becomes too much, if you're moving your hand too much, then your stick will fall out of your hand. But if you're moving just enough, your stick will stay balanced. Again, this batch normalization is acting on X. So the X is previous layer. That's pretty much. And let's incorporate a dropout at the end of it. So dropout means the model will randomly drop 20% of the data sets so that it will prevent from overfitting. So you don't want your samples to be overfit. Again, it's going to work on the previous layer X. So now what I'm going to do is I'm going to repeat this a couple of times. You could have used a for loop. One thing you want to make sure is you change this portion here as X, because it's going to keep working with the previous X, which is here. Like you don't want the input layer because input layer is in the beginning. I'm going to add another of these. So we got 3 stages, and then we'll incorporate something called flatten. So flatten is basically take a matrix and convert into like linear matrix. So flatten, and it's gonna work on the previous one, X. And then we incorporate a dense layer. Units, let's incorporate 128. You can do any number you would like depending upon your computing powers. And then 128. And next one is the activation functions, and we're gonna be using value. Again, it's gonna work on the previous layer. Let's incorporate another dropout. And let's again drop out 20% of your data. Again, it's gonna work on the X. So I think we are almost done with all the hidden layer, and now we are onto the output layer. So output layer is gonna be a dense layer. And units, how many units it's gonna have? So our possible number, our possible outputs are 10. So it's number of units is basically how many outputs you have. So we have 10 different digits, right? So that's why it's 10. And activation function is gonna be, as always, we will be using softmax. Again, this is gonna work on the previous layer. So don't forget this X, so which is the previous layer. All right, so that's kind of all the layers. Let's build the model. So the model is gonna be it's gonna be input layers and output layers. So these are the 2 things. So what's coming in? Coming in is I layer, which is basically this. What's going out? The output layer, which is basically this. And to get to X, this X would be here. Again, it's gonna be go all the way to the top, to the first convolutions. All right, so that's our model. Hopefully I didn't get any error. Okay, so no error. So let's compile our model. So model is gonna be model.compile, and we're gonna use optimizer, and we will be using Atom. Again, you can put the learning rate, you can manually edit the learning rate, but let's go by default because it's basics. And then we will add loss functions. Loss function is gonna be categorical cross entropy. Because why it's categorical? Because our number, our output can be only 1 values after these, out of these 10 value. So it can be only one of this. Like it cannot be like you cannot have 2 1. like 2 digits. It cannot be 7, it cannot be 8 together. It has to be either 7 or 8. So you got the idea of it. And the last thing we're going to be using our model is matrix. Matrix would be, it's going to be accuracy. And let's look at the summary, how many parameters we got. It should not be the MNIST data set. Yeah, we got 125,418 parameters. I went a little bit overboard with this one. Like, you could technically train the model without these two. It will be still above 95%. But adding these two kind of makes our model better. So that's why I did it. But anyways, this won't take too long because we are using our GPU to train. But again, if you are doing your CPU, if you are using your CPU and you want to make things a little bit faster, you might want to drop these two and also maybe drop from 32 to 16. Here, you can drop this to 128 to 64, maybe 32. It still be fine. You're probably going to see some drop, maybe 93, 94%. But today we are trying to get 98%. Okay, so this one looks good. So let's fit. So model.fit. And we're going to be using our training set, xtrain, ytrain. Batch size, how many batch sizes you're going to fit. We're going to pass 500 samples, maybe 1,000. I think I can handle 1,000 samples at a time. And how many epochs we're gonna do? Let's do 10. I know it's kind of overfit after 4, but let's see 10 and see how the overfitting happens. So and then epochs is 10, and validation split, again, we are splitting. Let's do 20%. So this means 20% of the data sets is not gonna be trained on. So it's gonna be trained on 80% of the data sets of the training data sets. So remember, we split it in the beginning by 60,000 and 10,000. So this is your training sets. Now, out of that 60,000, 20% of the data sets, it's going to be your validation data sets. So we can see how good is our model is doing there. So verbose equal to 2 means it will show us all the detailed number after every epochs. I think that's good. Let's hit enters. This would be super fast. You see, we already done. It took 2 seconds only. Okay, so let's look at here. So we are already at 90% accuracy score on our training set, and our validation is 95. So eventually we got 97, 98, yeah, roughly around 97, 98. So that's the point I was trying to go. Like, we want to get rid somewhere close to 98%. The reason this one seems slightly bigger than this number, because remember, this is only a small percentage of the number, and this is a larger number. So it's like, if you have smaller number, it's just basically law of large number. So if you have large data set, then obviously you're going to do a little bit more error than this one here. So that's why. So our goal was to get 97, 98. So I think we achieved. We can make this, I think I have tried this before with a little bit different parameters. I got to 99% sometimes, but 98 is pretty good. Okay, so let's do predictions equals to model.predict. And we're going to be predicting on the test data sets. And I'm going to do print predictions. And we will print the first 5. Let's print first 5. And then we'll do predictions equals to numpy dot argmax. And it's going to work on the previous prediction that we just did and find the maximum index. Axis equals to -1 on the last axis. -1 means last axis. And let's see print predictions. And let's print out the first 5. And let's print out the y test as well. So we can compare print y test. And again, the first 5. So let's look at our predictions and manually look at all the data. So if you notice here, so we got right here, so this is the first set of outputs. So we got 10 outputs and it's picking up. So that's our predictions. So we have 5 samples. So that's our first, this is second, this is third, this is fourth, and this is fifth. So for the first one, so we got 10 possible outputs. And what the argmax is doing is finding the maximum of all those 10 outputs and putting out the index. So for example, out of this 10, the maximum is the 8th index, so which is in this case 0, 1, 2, 3, 4, 5, 6, 7. Oh no, 7th. So this is 8th index, which is number 7 right here. So this one is 8th index. So you can calculate first, second, third, fourth, fifth, sixth, 7th, and 8th index. So 8th index is the highest of the 10. And what is the 8th index stands for? 8th index stands for number 7. So you can see our prediction is number 7. I printed out Y test as well so that you can compare. So what is our Y index? Y test tells us. Y test tells us the data set is actually 7. Same goes for number 2. So let's look at the second data set right here. The largest number is the 3rd index. So this is first, this is second, and this is 3rd. So the 3rd index is our largest number. Oh wait, I think I should have mentioned it before. So these are written in terms of scientific notation. So this is basically 9.99 dash into 10 to the power negative 1. So this one is 4.31 into 10 to the power negative 8. This one is 1.0 into 10 to the power negative 10. So the largest number is this one, 9.99 into 10 to the power negative 1. So this means this is the 3rd index, and 3rd index stands for number 2. And that's our number 2, and which is exactly our Y test also tells us. So basically it's predicting correctly our neural network. So let's find out the accuracy score and confusion matrix. So we can do that from sklearn.matrices. From sklearn from matrix, let's import accuracy score and confusion matrix. And let's do this. Let's AC score equals to accuracy score. So you need 2 things, actual. So our actual, in this case, the original data set is Y test, and your prediction, so which is our predictions. Let's print our accuracy score. Okay, next, let's do confusion matrix. Is confusion matrix. And again, it needs 2 things, actual value, which is Y test, and our prediction value. And let's print confusion matrix. And you could see we got pretty good accuracy, 98.31% were correct. So this is our confusion matrix. So let's convert this confusion matrix into a pretty beautiful data. And this data will make a lot more sense once I show you the number. So let's see, have I imported Seaborn before? Actually, I did not. So let's do import Seaborn as SNS. And so let's do this. Access equals to SNS.heatmap. We're gonna plot our confusion matrix. We're gonna annotate our data. So let's put that true. The format we will be using is D, and let's see, CMap. I'm gonna use purples today. That's pretty much all we need. Okay, so this seems reasonable. So let's add a few more things here. ax.setTitle. We're gonna be, I'll explain everything in a second. So let's call this confusion, title is confusion matrix for MNIST datasets. Maybe the font size, let's put 16, maybe 18. Let's put 16. Okay, and then AX set X label is gonna be, so the x-axis is predictions, what we are predicting, and let's call the font size is equals to 16. Let's keep it uniform. AX dot set Y label is gonna be predictions. Oh, Y label is actual. What is our actual? And let's keep the font size as 16. All right, so let's look at here. So that's our confusion. So let's try to analyze this data a little bit better this time. So you can see here predictions. So what this is doing is, so it's predicted. So it's predicted, okay, here. So it predicted 974 times as 0, and it turns out the actual number is 0. But it never mispredicted like any of the 1 as 0. But it turns out it has it's mispredicted like 8. So it turns out it says 0, but it turns out 4 times actually it is 8. So that's the data sets. So obviously in the diagonal, how many of them are correct, and on the outside, it's how many of them are incorrect. So you could see there will be high confusion between probably 3 and 8, because 3 and 8 sometimes looks pretty much alike. Maybe 5 and 8 looks pretty much alike. So if you notice 5, oh no, actually it did a good job. None of the 8s were predicted as 5. That's pretty good. So our model is doing pretty good. Yeah, 98% accurate. That means it is doing pretty fantastic. So that's all about MNIST datasets. Again, in the future videos, I will go over like how convolutional neural network works, and what is the kernel size means, and what are the strides means, what are the padding means. So these are like very higher concept. Those needs one video on themselves. All right, so that's all I had to say in this video. Let's say bye and stay tuned for more. I haven't done any biological applications of deep learning, but I'm slowly moving on there. So please stay tuned.